myšlení zítra? Jste tam na firmě nebo?
Jo, nemáme auta. Přijedou 9 tuny.
Přijedou 9 tuny, takže tady.
Proč není auto, že?
No svýho, no.
No, někomu můžeš říkat na chvíli. Ukládat. Protože to asi budou muset všichni.
No, docela hafon.
No ne, tak kluci mají tady jaké auta, to se nebojím, že se nevejdeme.
Ale jakože na vyložení toho bude hafon.
Všechno. Ale tak víc ne, to jsme třeba mě 9 tuny přijedou a já doufám, že se nám...
3 9 tuny nebo 2 přijedou?
Co?
3 nebo 2 přijedou? 2.
Já doufám, že se to tam jako...
Rašelina.
Já doufám, že se to tam natlačí, že to nebude muset se jako točit. No.
Že asi bude muset.
No, možná ne.
A budeme to tam muset sázet fakt jako...
Já třeba přeseknu kabel, protože začne, když je porušen na reku, třeba budeš muset za běhu nějak rozmontovat. Což nám zase, když si přijede čtvrtý ten mikrofon.
Jo, ani sám nevíš.
Ne, ale pánové, se nás tady vám vezu spěšně kurýrem. Opravdu mikrofon, máte se tam okamžitě namontovat. Já v pohodě. Zaběhu. A bojíte se, že jako... Ne, nebojíme se. Přišel můj čas.
Honda, čuchni. This is the first piece, yes. Hello?
Work. Is this compatible with the glasses?
I don't know. Yeah.
Okay.
And this is the auto.
Okay. I'll set. Wow.
It's okay?
Yeah. I hope this doesn't come off. Sure. Okay. Stuff. Good, yeah. Okay, now that's good. I'm not sure about the... No, it's
Good afternoon. I think it's time to start our session. Welcome everyone to the session, Future Networking Challenges and Opportunities. Today we'll have three presentations. The first presentation we'll hear about the recent discussions, results of recent discussions on architectural strategies in the research networks. The question statement given in the first presentation, which is circuits versus packets, is still relevant for the research community. The first speaker is Simon Leinen, well known to the community. He works at Switch as a network engineer, and he's responsible for the design and operations of the national packet backbone.
Thanks, Bartek. So, welcome, ladies and gentlemen, and I'll be talking about something that was a topic at TNC 2006, I think, in Catania, where we had a panel on this with a lively discussion. And apparently some people are still interested in this. I know I am, but I also got some feedback lately that this might still be a question of some relevance. So I'll open with some background and then try to dissect this question a little more into some more manageable pieces. Then look back over what has changed and what might affect the outcome of this debate lately, and also give an outlook on what I think, and this is certainly subjective and open for debate, what I think we should be working on as the NREN network building community. So, as I said, the motivation is that many of us in the NREN community, we face these architectural big discussions on how we want to build our networks, and especially in the European NREN communities, we have this long tradition of trying various connection-oriented technologies. There's a list here, and I had the impression that these are coming and going fads, and what sticks with us is this packet network that, like the internet, that we have to provide our users. But somehow, sometimes I get the impression that we do this reluctantly, although it's our bread and butter, and what actually customers have proven to be, or customers, the research community users, at least in our country, they seem to be willing to pay for. So, but why are we always looking at these other services and trying to understand this mostly? So, of course, one of the reasons is that we want to differentiate ourselves from the commercial competition, and it is questionable whether we can just do that by providing a better internet than commercial suppliers, or whether we have to cater to different communities. So as I said, I got some feedback that people are still interested in this. I hope we have some discussion afterwards. So about this packets versus circuits discussions, I think it's actually two sub-discussions that come up when I discuss this, or when people discuss this. One is the shape of the service that we provide to our users, and maybe the two extremes are an any-to-any service like the internet, where you get a single connection and you can talk to anybody. Okay, that's the usually this is under a best efforts regime, and it's hard to guarantee, or usually users don't get any specific quality of service guarantees, but then they get a very large set of people to talk to. And the other extreme is, a single point service is not useful. It's not a network service, but a point-to-point service, something between 2 points, is sort of the other extreme. And then between that, you have multi-point services for small groups. So I lump these together as under small group services for small groups, build tiny, small networks for well-defined communities. And these often do have quality of service guarantees. The ones we have in Switch actually don't, but people still want them. So, okay. So what I often struggle with is what should we build? What kind of network should we build? And if you look at these alternatives, the any-to-any network, of course, it has this value that it's big and you can talk to anybody, and that sounds like trivial, but it's actually a pretty powerful thing. Robert Metcalfe expressed this as Metcalfe's law, that the probably most of you know this, that the total value of a network increases with the square of the number of connected nodes or people, because it creates n times n possibilities for two people to interconnect. And there are various variations on this. Some people claim that the value, that the increase lowers down over time because you get more noise. Other people say, no, it's even more exponential because you cannot just have combinations of two people communicating, but arbitrary subsets and so on. But trivially, a big network is in some way more valuable. What we found when using the internet as an infrastructure for research is that there are some typical pain points. Today, I think the most important of these are the choke points at the campus boundary, where there are devices like firewalls that enforce policy, which may work for a subset of the university and is probably constructed according to the needs of a small subset of the university, and that hinder certainly the highest end forms of research usage of the network, but maybe also some of the middle ground. And also, it's a problem getting sustained funding for something that has been like accepted as something that's just there and a diffuse thing. It's also when you want to offer some increased quality of service guarantees, and that becomes harder in such an environment. So the other type of service, the few-to-few services, it's obviously easier to do that to, for example, using light paths or so to build small subnets with very high quality of service. So that's an advantage. Some customers like to be isolated in their groups. That, of course, technical reasons for that. I think they mostly have to do with the way that these security enforcement, policy enforcement is built in campus networks. But it's also something that is just reassuring. So it's, I'm not sure how much of that I generally accept when people say, I need isolation. I think it's always worth asking what exactly do you mean with that. So and of course, these networks, it might be, it's possible that for some really special applications, such as maybe the LHC, which is a unique infrastructure in the world, then you could really save some costs by having separate infrastructure because you can optimize for that case. Of course, that works if the case is well known in advance, then it will work best. Otherwise, it might be better to have a less optimized system that is that can be easier evolved to the changing requirements. So, looking at this from maybe even higher level of an organization that has to make these choices. So, the one approach will be to segment the users so that you can treat them better. And a common approach seems to be that, well, the internet connectivity is obviously something that people want. So we don't quite understand why they think they need this, but obviously they do. So we give them just enough so that they can work. And we define this once, how much internet you need, maybe access to web pages or something. And then you have the big science users, or the science users, but mostly it's the biggest users that get really good connectivity because they want to do advanced work. And I think we have established a sort of symbiotic relationship between the research networking community and these big users who are used to getting funding on a very large scale for big infrastructures. High energy physics is an example. And so that is something we know how to get funding for these infrastructures. For me, that's a possible explanation. It may not sound very nice, but it's a rational explanation why we see these kinds of networks being built. So another approach will be to just ignore this segmentation as much as possible and try to provide just very good connectivity for everybody. And my principal motivation for being in favor of that option is that it creates much more potential for new ideas to surface. Things like the web being invented, or whatever, BitTorrent or Facebook. That's the internet. The general purpose internet is just, and especially the parts that we operate, which are just higher performance, is an excellent breeding ground for this. Now, I always think back of last year when Anthony Joseph from the Berkeley Red Lab presented the vision statement of that institute, which was to enable one person with a great idea to design, run, and operate the next generation internet service over the course of a long weekend or something. And I thought, well, this is really a nice vision that I could share. But how much of this vision do we, as the NRAN community, think of this vision? We don't think of individual users with bright ideas, right? We mostly deal with vested interests of user groups that we like to serve. So, and of course, there are some efficiency arguments for having a single network. We learned that yesterday morning, that this was even formalized in Peter Denning's PhD thesis in '68. Large capacity pools are more efficient. I claim that we could build these things so that they would scale to high-end users and still be cost-effective. And I call upon you to work on this unifying vision. So there is, of course, another important dimension of this debate, and I will cheat a little bit by not talking much about this, although it's like the core of the connection-oriented versus connectionless debate, namely whether you forward individual datagrams or you forward data inside connections. Fortunately, also at the same talk yesterday, we heard that from a technical point of view, that debate has been settled and packets win. Yay, packets. But someone else commented very quickly on Twitter that, well, maybe he will be coming back to us in 3 years and just say the opposite, because by then they will have a new product to sell. Who knows? Someone else gave me feedback. Well, this is just a pendulum that swings every few years. We have to do this. We have to do packets and then circuits. There are technical reasons for that, I hope, but I have the impression that most of them will go away. I'll come to that later. So what happened since we met in May or whatever, or June 2006 in Catania? Well, a couple of news bites I found. Interestingly, 2006 seemed to have been, to me, I didn't try very hard to make this up, but there are a couple of events in 2006, just after our discussion, maybe because of our discussion, that are sort of an inflection point on the way to this multi-core world, you know. So Intel gave up trying to get more single-core performance out of their processors and moved to a completely different architecture with less instruction level parallelism and so on. You see this reflected in the supercomputing world also over the last 5 years. The number of cores increased by a factor of 10 and the performance by a factor of 20. So the biggest part of the performance increase also in that space is due to more parallelism. Also in 2006 there was this white paper by the same people who brought us the wonderful Red Lab mission statement, explaining or laying out the research tasks for making this multi-core world reality. I found this very exciting as a computer scientist and one of the real big new things that are happening. And also in 2006, right at the end, we had the last improvement of the Internet 2 land speed record. The land speed record is an ongoing competition that rewards the fastest over a longest distance single TCP connection, calculated as throughput times distance. And somehow this result was so good that nobody bothered to try to improve it. I think it was too close to the limit of 10 gigabit links, because you have to provide some minimal increment, minimum publishable increment. And I guess it's also because people thought, well, what is this single thread TCP bandwidth really worth? I hope. So we are really into this multi-core or many-core revolution, and people are trying on a global scale to revisit their software and hardware infrastructures to leverage this, because you won't get faster cores in general. The core speed still grows, sometimes increases, but very slowly. But you get more cores. You get as many cores as you want. So even in networking, we notice that. And also, if you look at the traffic in LHC or large grid interconnections, the traffic between large grid sites, you don't see multi-gigabit per second TCP connections. You see bunches of connections, each running at relatively moderate speeds, a couple of 100 megabits per second. So this is very interesting because it makes the the high-end research traffic much more like internet traffic. So it's hard to, from a distance, to distinguish this from a couple of thousand people watching YouTube or something. And for the people who build the network, for us, it opens up new possibilities. I really like this because it allows us to use legitimately parallel links inside the network and build the network in a way such that it scales out by adding parallel resources rather than having to scale up to be able to satisfy these high-end requirements by buying bigger and bigger boxes. And what we learned from cloud computing and supercomputing is that scaling out is generally cheaper because you can leverage high volume components and so on. So for me, this is like my provocative question is maybe if we can get into a regime where you can just increase the packet network by adding stuff and then moving to higher link speeds as they get cost effective, maybe we don't need this connection-oriented networking, because in many cases we had to use it as a stopgap because our high-end users, they needed 10 gigabit line. They always need to fill the link, right? And in an initial step, it's expensive. You pay the early adopter premium for the fast new link, so you can save something by not doing packet switching. But I have the impression that we can get out of that regime and forget about the next generation, whatever will come after light paths. So also other mega trends that are happening is the move to cloud computing. There are these huge infrastructures. There's a lot of hype around it, but if at least some of that hype materializes in useful services, and there are some signs that this is happening, then this is also work for us because researchers will use these infrastructures. Currently, they're all in the commercial world, so this is a task for us to build connectivity to these commercial infrastructures, and I think there are the obvious way to do that is by providing enough internet connectivity. Also, some of us are considering building infrastructures for their own constituency, cloud infrastructures, and that poses all kinds of interesting networking problems. So there's always also been a lot of revived interest in data center networking, probably driven by these huge clouds, and both from the commercial world, but also from the research world. like wonderful new architectures of how to build Ethernet networks with hundreds of thousands of nodes that don't have problems with address learning and large bisection bandwidth. Some of the products that come out could be really interesting for being abused in the backbone, because one thing that was added to Ethernet is shortest path routing, which is something the absence of which always prevented me from thinking about basing, for example, the national Swiss backbone on Ethernet, is that I don't want to give up shortest path routing between sites. And now you can get that in Ethernet. So I'm looking forward to the third talk in this session, because they will talk about how to manage large Ethernet infrastructures. I think it's mainly hinges on whether we can manage these things as well as IP networks. But it is also a possibility that the new silicon that you can get to build very, very fast Ethernet switches, whether that can also be used for routers, or whether that will be used in commercial routers. One way for us to do that is to use OpenFlow. So OpenFlow has been talked about a lot in the past weeks, because Internet 2 made an announcement that they will provide some OpenFlow-based infrastructures and opening that up to researchers. The main commercial promise for OpenFlow is that you could build very large data center network with a single controller. I think that is not very interesting for the backbone. But someone could come along and build a nice operating system that would allow me to buy an arbitrary cheap OpenFlow Ethernet switch from China, also, or Taiwan, or wherever, and then still have the software to use it as a normal router. So that would be for me an avenue to get cheap routers again. There are also things that are not new frontiers, but that still have to be done. And I think in the research network community, we sort of are in a very good position to do these. Getting IPv6 off the ground, for example. We've done a lot, but not so much lately, at least not together. Some in the countries, yes. Approaches to scalable routing in the internet. There's a lot of work and discussion in the industry and also in academia, including European academia, about these approaches such as Lisp or ILNP and others. But the NRANs are curiously absent from all this, our community. Also multi-domain multicast, which is one of the big achievements that we built. We should make sure that this remains available for interesting, exciting applications in the arts and elsewhere. And also, we should work on these problems that prevent high-end science usage on normal research network connections now, such as how to do sane perimeter security or security inside campuses. Or we can also just do nothing and see that the internet is being replaced by just everything using HTTPS and all the services running in commercial clouds. I think that will be the alternative universe, which is maybe not too bad. And there are also, I'm not claiming that the internet is perfect. It needs things to be fixed, and it's also worthwhile thinking about alternative approaches. And the EU has been funding that a lot. Also, without us, mainly. For example, one symptom maybe is that the EU organizes this big Future Internet Summit in exactly the same week where we have a high event. It's probably just bad luck, but nobody noticed, right? That's a sign. So there's funding for this. There's Genie in the US. There's a lot of, well, it's just funding and people meeting because there's money, but there's quite a lot of interesting work, and we should at least follow that. I know some of us do. Some of us are not here at the moment because they're in Budapest for that thing. One thing that I really want to point to is content-centric networking, because that is a very fresh approach. It's not based on connections, but and there are also European researchers active in this. I think we should work with them. So my favorite project is to give up more control from the network, except for looking for ever new methods of tightening controls in the network, namely the control over which path the packets take through the network. I think that really fundamentally this should be left to the hosts, at least the choice. That was actually an initial idea of the end-to-end mafia. Before they applied that to TCP, they thought they could apply that to routing. It's something that has never really been tried. So there are really some exciting things that still have to be looked at. And also, of course, we should help the people who are in these projects and try to experiment by providing the infrastructures. I think we have done a good job, kind of good job with Federica and similar things using virtualization. But we should also try to just tie closer links to researchers. There used to be a more free flow of ideas between the research community and us and the industry. And I think we could get that running again. So, sorry for the haste, I had too many slides. I think the pendulum has been swinging back. It's not too bad. We can focus more resources on internet-like networking. There's a lot of work, exciting work. I think it's important for us to be to attract people from research. And there was some discussion that we have sort of a recruiting issue. And I think by focusing our resources more on this, it will get fresher and we will get more relevance in general. So thank you for your attention. I hope we can have some discussion.
Thank you, Simon, for interesting presentation with a bit of history. Are there any questions to the speaker?
Hi, Simon. What I miss is the purpose of why we're doing circuits or packets at all in the first place. Who is this for? And currently, these users will come to us and ask us for a circuit. How do you propose getting to the point where they just come to us and say, help us with our research, help us solve our problem, and then we're free to do all of these things that you say to bring packet networking forward again?
Yeah, I guess it's working closer with with these researchers and trying to understand the real underlying needs. I think currently the debate is sort of flawed because of these of the realities in how the funding works and so on, and also misconceptions about connections. Of course, probably you expected to hear more about these fundamental issues with connections, but I don't know. For me, this is a big public relations issue. We have to get over this easy way of selling connections.
Hi, Thomas Schmidt. You were in the middle of your talk. You were pointing to parallelism. I mean, to the parallel flows. And my question would be, if you look at these, I mean, which you were also addressing these high-end users, are you pointing to something like resource pooling as a solution for high-end flows, like using multipath TCP or stuff like this?
Yeah.
Is
so
that what you're actually headed at?
Multipath TCP is one exciting possibility of leveraging parallelism because it could work within a box that has many cores. I think currently we already see many parallel TCP connections between the same hosts or a single host and a set of hosts that I assume get distributed internally over multiple cores. So probably for these users it's almost as good as multipath TCP. Just multiple TCPs.
I'm sorry that the time is flying and we have the next two speakers, so I propose to continue this interesting discussion offline.
Sure.
The next presentation raises a number of questions, significant questions on the impact of decisions made at the beginning of Internet. The speaker, Edward Grassa, he's a researcher at I2CAT. His main interests are bandwidth on demand services, network management. So Okay, let's wait a minute for the speaker. Okay. Okay, problem solved.
Okay, thank you, Bartek. So the work I'm going to present is a collaboration with Boston University, the Waterford Institute of Technology, and a startup called Tria Network Systems. But like 99% of the ideas presented here, if not 100, are the merit of Professor John Day. So what I will try to show here is, or I will try to convince you that the current internet architecture based on functional layering and TCP/IP is not complete, and therefore doesn't provide a good framework for resolving the current issues such as mobility, multi-homing, and so on. Therefore, we need to move away from that. Moreover, that there were networks in the past, in the 70s and the 80s, that had a better structure than the current TCP/IP based architecture, and there were lessons to be learned from that seems to have been forgotten. And finally, introduce a new architecture that provides a better structure. It tries to research what are the fundamental principles of networking. If computer science is a science and networking is part of it, what are the principles? And RINA tries to be the architecture based on those principles. So let's get started. We have plenty of material to cover. So let's start with naming and addressing. So let's just look at this simple scenario here. We have two hosts. One of them is multi-home, so it has two interfaces connected to the network. And the left host is just has a web browser, and it's just retrieving a web page served by the right host, which is a web server. And so it's just you put in the DNS name or the IP address here and retrieving the content from there. But one of the interfaces fails. And the problem here is that even if the host is multi-homed, the network has no way of knowing that the two interfaces belong to the same host. So this is the first fundamental issue with IP, that it is routing based on an address that is not the final destination of the request, but is in the path to the final destination of the request. So we have computer network, right? What computer networks communicate is computers that are hosting applications. Applications are on hosts, so the obvious solution seems to be okay. Instead of routing on the interface, what we have to do is naming the hosts and route on the hosts. So in this scenario here, we have, instead of having the network route on the interface, we are naming the host. So we have host H1, host H2. May have one or more interfaces, but if the identity doesn't change because of that fact, and the network is calculating routes based on the final destination of the packet, which is the host. So in this case, the node namespace is completely independent of the interface. And in fact, the interfaces is just a local matter, right? It's just a way to differentiate multiple paths between adjacent hosts. So it doesn't look like a very complex solution. It seems nobody realized before, and the answer is yes, of course. So ARPANET, which is the basis, was where this decision of naming the interface comes from. They had very early in 1972 a use case where an Air Force base wanted to be multi-home to the network, and they said, okay, this is not going to work because the way we are doing it right now, we don't support it, but we know how to do it. There were after that other initiatives, like the French network CICLAT, 1973, that was very aware of this and solved it from the beginning. And apart from that, there were XNS, DEGNET, OSI that also had this solution already from the beginning. So they were supporting multi-homing for free without the need of any special protocols. We had the chance to solve this with IPv6, but as the RFC 4291 points out very well, IPv6 addresses all type of IPv6 addresses are assigned to interfaces, not nodes. So we continue with this fundamental limitation. Apart from naming nodes, another question here is, okay, does the properties that we assign to these names matter? And the answer is yes. If you have a small network, maybe it doesn't matter so much because the scale is very low, so you can just, I don't know, use simple enumeration for the nodes like node 1, node 2, node 3. But as you start having bigger and bigger networks, if you choose the right properties for names, it facilitates the scale of routing a lot. And one of the properties, or the most important property a node name needs, is it has to be location dependent. So it has to be an address, right? But not so. By looking at the identifier of the node, if it's an address, you will have some hints of how to get there, of where it is. Sorry, just by looking at the name, without the need of calculating any route to it. So the nodes have to provide a meaning of where the node is in that network, but not an absolute term. So do not think about geographical location here, but in the topology of the network, where is that node in respect of the others? So that means that nodes that are closer should have addresses that are similar than nodes that are farther apart. And another important way of making this scale is if you organize the node namespace based on a hierarchy, you also remove the need for having to know all the default routes to everywhere. You just need to, the routing tables just need to keep the shortcuts of on this hierarchy, because the node name already would provide a default route. For example, if you have this example of 3 networks, 3 levels of networks organized in a hierarchy of campus network, metropolitan network, and regional network, the key should be regional. If you have your address be organized hierarchically, like with some part identifying the region, some the metropolitan area, some the campus, and finally the node, you always know what region, what metro, what campus the address is at, right? So you can always, by just moving up and down the hierarchy of layers, reach that node by default. Of course, if you have shortcuts in the hierarchy, you can reach the node in a faster way, or you can reroute around areas of the hierarchy that may not be working because the nodes are down. So comparing this to IP is routing on the interface that we have said, and so this makes scaling difficult. First of all, because if there are more interfaces than nodes, each node has usually more than one interface. In the case of routers, even if we move closer to the core, usually it's tens or hundreds. So these are more routes to maintain. But what is more, IP addresses are not location dependent at all. If you just do a simple trace route, for example, like this one, you will see that every time you change from network, the IP addresses are more or less random when compared one to other. And this is because IP addresses are assigned on address blocks based on the provider, right? Not on where the nodes of that provider are in relation to the other ones in the network. So that makes routing and scaling very difficult. And also that makes an IP address just real name, because it's not optimized for routing and it doesn't provide a sense of where. Another issue in naming is application names. So what we have, if we use this URL, for example, it's just pointing to an application which is serving web pages. What we will see here is the application name is composed by the DNS name with a host name, which is just a synonym of an interface of the host. And it has in this one is implicit because it's port 80, but it's also using the socket endpoint of the TCP connection. So what we have is a static binding between layers. So now if my application is moving to another node, its name will change. It's just the property we don't want, because if we don't want mobility, if we want applications to support mobility, their identity should remain the same regardless of where they are. So what's the solution to this? Very simple again. We need an application namespace that is independent of the node namespace. And at the end, this is about application-to-application communication, right? We don't care about where things are. We want to communicate with this instance of Skype represented by a user, or with this web page. Users don't care where these applications are. So what maps the application to so that the network does care, of course, because it has to route the packets from one request to the other application. So then the network has to maintain a directory that maps what applications are on what nodes. And when the network is asked to reach a certain application, it will query this directory and know to what node it has to send the packets. So again, this seems not very complex, and there were like CCLAD, XNS, DECnet, and OSI had also understood that you needed an independent application namespace. We have mobility, which is really a desired feature today. But we can just think of mobility as of a dynamic version of multi-homing, right? As your node moves through the network, it's dynamically acquiring new points of attachment, and it's when you move from a wireless antenna to another one, for example, there is a moment that you are multi-homed, and then as you lose power in the other antenna, you continue your way, you stop being multi-home, and so on. So if your naming and addressing architecture supports multi-homing, you have mobility for free, right? You don't need any special protocol to support mobility as it's done today. Again, because these networks in the past had this complete naming and addressing architecture, mobility was supported. So just to recap on naming and addressing, we need application names, we need node addresses, and we need also point of attachment names. So they are the least important of all, because they are just a local matter between adjacent nodes. We need directories that map application name to node addresses, and we need to route based on the node's address to make the routing system scale. And paths finally are just a local matter. It's just a local decision of one node how to reach the other node. So we can see routing as a two-step process. We calculate a sequence of nodes, and then at each hop we decide which is the best path to reach the next node. So this is just, this doesn't mean that forwarding is a two-step process. This is the mechanism required to generate the forwarding table. Forwarding is just still a lookup. And again, recap on name and address properties. Application names have to be location independent, so the application can move. Node addresses have to be location dependent but path independent, so they have to explain where the node is without explaining how to get there. And point of attachment addresses just need to be unambiguous between adjacent nodes. So what I think, let's just stress something that we think is important, is that in the 70s we had networks that supported all this machinery, and they seem to have been forgotten in the past. So if these issues are really so important, we should make an effort to go back and see what were the lessons learned by this network. And again, these principles doesn't seem quite complicated. So as usual, as you all know better than me, it's not just technical reasons what drive what are the architectures or the technology being adopted. So you know it's always complicated. So after naming and addressing, assuming we had done naming and addressing right, is the current layering we use the right structure or not? Let's see. So this time it's just not TCP/IP. It's all the network architecture so far have assumed that functional layering is the organizing principle. You all know about functional layering. So each layer is supposed to do a single function and provide this function as a service to the layers below. And all the architectures have a fixed number of layers that span from 5 to 7, depending on the model. But the more accepted ones are the physical, the link, network, transport, application. But of course, you all know that there are this model doesn't seem to work very well as an organizing principle, because there are functions that are repeated at different layers, like error and flow control, which is done in data link and transport. Routing is done in several layers. We have a spanning tree at layer 2. Now we have also open shortest path at layer 2. We have OSPF and the routing protocols at layer 3. We have protocols that we don't know where to put them. So MPLS, it's always the example of, okay, it's layer 2.5. But here there's no layer 2.5. Everyone has its own definition of layer 2.5. So again, we are not using the principle as we should, so it doesn't look like a good principle. There's also a handful of layer violations. Like example is the TCP pseudo header that uses layers data from the layer below to compute fields in the same layer. So it's breaking the black box metaphor. So indications of that we need a better organizing principle. One simple way, or the first thought would be to say, okay, so no layers at all. But then things look also doesn't provide a solution out of this, because if there are no layers, it means that protocols have to be efficient in the whole myriad of scope. So protocols have to be the same instance of protocols have to deal with resource allocation on a single link and the whole internet. So what the nice feature about layers is that they provide a divide and conquer approach, because they isolate different scopes of shared state. Okay, so we can have a layer that is just cares about doing resource allocation over a link. So you can really design very specific protocols for that layer. We have another one that is doing the same, but on the network layer. Again, you can adapt to this. We can do the same at the internetwork layer, and so on. So they seem to be a good principle. We maybe should just use it in a different way. So an important thing here, that a principle and a guiding principle that we will adopt, is that as networking is just used to communicate applications running in different computer systems, we can see networking as distributed interprocess communication. If we look at the left figure, we have what is commonly known as IPC, so with just two application processes, A and B, communicating in the same system. So you can use shared memory, local queues, and so on to achieve communication. If we move to the middle picture, which is a slightly more complex scenario, we have two hosts that are directly connected through a wired link. And here we can do also IP interprocess communication over a wired link. But things here are more complex because you need to synchronize both ends of the link. You need to do error and flow control because it can be lost in the link, and so on. If we switch to the even more complex scenario of the right, we have two hosts connected by an intermediate system. And we keep the layering metaphor. So if we have something that does interprocess communication over a wired link, we keep it. Then at the right, extending it, we have the same layer, but in a different instance that does the same interprocess communication, but is optimized for a wireless link. And on top, we can have another layer of interprocess communication that sits on top of the two lower layers to provide IPC over the full network here. So the important thing here is that the service that is providing that all these layers provides is exactly the same. It's application A wants to talk to application B. So I don't care how you do it, connection or connectionless, doesn't matter. I just want to communicate with another application given a certain quality of service. It may desire a certain bandwidth, a certain delay, certain jitter. So we can see that here there's a repeating structure of distributed applications that are doing interprocess communication at different ranges of scope. So we can see networking as distributed interprocess communication. And I think it's better to explain it with this picture. So this figure tries to provide an example of the architecture. We can see the vertical squares are systems. So we have a host, a border router, an internal router, another border router, and another host. And the horizontal squares represent layers which are doing IPC. We call them DIF as a short name for distributed IPC, interprocess communication facility. So let's take just the upper layer to see how this thing works. Each layer has an instance at each system, which is just an application process, because all the entities in computing systems are application processes. It just happens that it's specialized to do IPC, so it's called IPC process. If the application process S wants to communicate with application process D, it will use the APC API and say, okay, allocate me communication resources, we're calling that flow, just to call it something, to talk to D with a certain QoS. I don't know, this bandwidth, this delay, and so on. As we've seen in naming and addressing, the node A1 will just say, okay, we'll have a directory that says D is node A4, so I can now establish, depending on the QoS that this one has required and the QoS that the layer below is providing me, I can decide what mechanisms I'm using to deliver the QoS. So I can maybe set up a connection with error flow control. I may just set up forward the equivalent of UDP packets, so no error and flow control. So this is a decision that is completely internal to the layer, because applications just care about communication, not connections or connectionless. So we've seen the structure. Let's try to dig a bit more inside. So what's inside a diff? How are these distributed IPC facilities? If we look at what we have to date inside the layers, we see that just the lower four, because they're more interesting for networking, we see that we have, in each layer we have one or more protocols, because each layer is doing a different function, so kind of makes sense that there are different protocols in different layers. But we can notice, if we look at a bit at it, we can notice that there is a repeating pattern on the layers. So in the physical layer, we kind of rely on multiplexing over the physical media. In the data link, we are providing error and flow control over the link network. We are doing the same, relying on multiplexing, but this time over different links of different technologies. Sorry, oops, this false, so it should be transport, sorry. And in transport, we do host-to-host error and flow control. This pattern kind of makes sense because every time we are relying on multiplexing, we are introducing the opportunity for errors to appear, for packets to be dropped, for memory errors to happen. So it's logical that the layer below doesn't trust this layer and does error and flow control. So what about diffs? If we compare the recursive structure to the functional layering, so here in both pictures we have three systems, two hosts and a router in the middle. We can see that the functionality is provided by a first level diff, so a diff that is sitting on top of the physical media. Is kind of the same as the physical data link layer together. And if we look at the functionalities provided by a second level diff, we see that it's kind of the same of the network and the transport layer together. So what a diff has to provide is, as we have said, distributed IPC, distributed interprocess communication, but that means that it has to rely on multiplexing over underlying diffs or physical medias and error and flow control. It doesn't need to do all of this, but it can. So you could instantiate a diff that just does rely on multiplexing and doesn't do any error and flow control at all. This depends on, again, on the QoS required by the application and the QoS provided by the layer below. Another important finding is that today we have, every time we have a slightly different physical media, for example, or a slightly different application, we think of, okay, we need a different protocol to be optimized for this application. This is why we have we have different protocols for different physical medias. We have TCP and all of its variation, and UDP for different requirements of the applications. But again, if we look at it with detail, and we try to separate the mechanism of the protocols from the fixed part of the protocols from the part that is configurable, we will see that maybe there are not so many protocols. By mechanism, we can, so that our transfer protocols just provide like 20 or 30 different mechanisms, like addressing, relaying, multiplexing, ordering, fragmentation, and so on. So if we allow for a protocol to be configurable with policies, we just need one single data transfer protocol. I will get a bit of water, sorry. Okay, so we just need one single data transfer protocol and different policies to configure it. So what's inside? Well, how many protocols are inside a diff? So there's just a single data transfer protocol that is configurable through policies. And configurable to what? Depending on what is in the ranking of diffs. If it's closer to the physical media, the policies will optimize this diff for this physical media. If it's closer to the application, the policies will optimize this diff for the application. And apart from that, an important thing is that because each diff is a distributed application, it needs to do a lot of synchronization. It needs to do flow allocation, it needs to do routing, it needs to do authentication, it needs to do resource allocation. We call all that functionalities layer management. And we are, again, because this is a distributed application, we need a protocol that IPC processes use to perform these functions. We call this protocol CDAP, and it's object-oriented. So we use different objects to perform these different functions in a distributed fashion. Here are a summary of the diff characteristics. So it has a complete naming and addressing structure. It has a configurable error and flow control protocol. I didn't speak a lot about that, but it also supports quality of service by isolating the quality of service interface from the way of providing it. And very important also, it has authentication and access control. So if an IPC process wants to join a diff, it needs to be authenticated before being able to join. This also is configurable, so for less security requiring diffs, it may require no authentication, but for some very secure diffs, you may have strong authentication and PKI. Okay, so even if you were convinced how we make this happen, how we can migrate to this. And the good news is that we don't need migration. We just need to adopt it. So we can start small, which is what we are trying to do right now with creating the first prototype of this architecture, and on top of TCP/IP. We do this because to show two things: that we don't need any complicated adoption migration strategy, and also because TCP/IP provides sorry, a very flexible substrate, and it's easier to code a diff sitting on top of TCP/IP than a diff on top of the internet. And once you have this, you can push the diffs down through the layers until it reaches the physical media. So just to conclude, I have here this picture of the RINA poster we have at our booth that I took at, that tries to make the main points that differentiate what we think is a complete architecture from the ongoing demo that the current internet is. What we really appreciate is that we challenge you to find a better or simpler structure, or to work with us to explore where this recursive internet architecture can lead us. Tomorrow it happens to have a talk of John Day at Barcelona. The bad news is that it's the same schedule as tomorrow's closing plenary, but the good news is that it will be recorded. So if you are more interested in it, please, you can follow it, the recorded session from this URL, and I think you should do it because John is a great speaker. So thanks for listening, and if you have questions, I will take them.
Thank you, Edward. Indeed, interesting talk. Are there any questions to speaker? Yeah.
Hello. I have actually two questions. First is you didn't really speak about the binding. I mean, in general, we agree that it is really nice to address an application somewhere. I don't care about where it is. So I open a communication channel to an application name, but there's must be a very complex process of binding to actually contact this application, binding to addresses, and so. The second question is this recursive architecture. I mean, there is a proposal like 10 years old by Joe Touch. How do you differentiate from this? That looks pretty much the same.
I would argue that it's pretty different, but okay. So about the first question, an application, there's two ways. So an application can make explicit registration to that node. So okay, I'm available through this node, which also allows not all the applications of a node to be available to all the networks. So an application can choose through which network it is available. Or you could have a policy that all the applications in a given node are automatically registered by the operating system to that node. So the node would have its directory populated with all the applications of that node, or from the ones that register. I cannot.
So you're saying you have a global directory of applications, is that it?
You need a global namespace for applications, but not really global. Also, it depends on the scope of the networks you want to communicate. As now we are used to think about the internet, but you can have many parallel internets. So
But given the previous speaker, he said that the vision of the internet, or the good thing about the internet, is that it has n-square value. So every application can talk to every application. So then you would need a global directory of applications, right?
Not global. It's depending. So because even today you have private networks, right? There are not all the applications want to communicate to not all the applications. You can have one diff that is the equivalent to this public internet. So you will have global, but okay. And about the other thing, what the work of Joe Dodge is about, it's more about recursive stacks of protocols. So there are a lot of insights that this architecture provides that we think that this work didn't provide, like the naming and addressing, like the guiding principle that we can set and working is interperson communication, and many other things that I didn't have the time to talk about in this talk, like separating portal location from synchronization and so on.
May I have a comment? It was a very nice presentation, but I think this kind of architecture is already built with several locations. If you are looking at the middleware initiatives, even from the grid or cloud community, they are building directories, and they are building for example, the search engines. If you look at the search engine, it's kind of a directory for you. So I think everything is building at the moment in the internet on top of the HTTP level. So basically, what we are doing, maybe we can optimize the layer below. And also, if you look at the HTTP level, most of the middleware solution or the grid and cloud middlewares are focusing on RPC, the different kinds of inter-process communications. So I think this is something is very similar.
Yes, as I said, the naming and addressing part especially is from the 70s, and it's in many other distributed applications use it. So we just, if we get the internet to use it.
This is not correct. Even as grid uses a specific protocol for data transfer, grid FTP, and cloud is doing the full spectrum of specific protocol for connecting blobs, data, and storage. So HTTP will remain as a management protocol, but for data and for lower processes and synchronization will be completely different. And this may be the solution, but I'm not commenting about.
Yeah, so if I can make just a last statement. Okay. So the point of this is that what we are researching is to find the simplest and have the less number of principles that lead to a simplest architecture and simplest implementation. It's not about putting one piece from here, one piece from there, but getting the full thing working together, because taking one thing from there and one from here doesn't work.
Thank you. I'm sorry, I need to stop the discussion at this point because we have the last speaker in the session. Now we are moving more to the technology. The last speaker will be presenting management functionality for Ethernet networks, specifically monitoring. The speaker, Mark Prince, he's a researcher at the Dutch Organization for Applied Research, TNO. He works in the area of future internet, specifically on IP and Ethernet network architectures.
Okay, hello, welcome. Today I'm going to talk a little bit about Ethernet operation, administration and maintenance, or in short OEM. It is the result of a small study we did last year. Actually it was me together with Risha Mohta from ServNet. And it was about looking at what Ethernet OEM is and what it could do for the NRN community or for ServNet. Then the question is why we're even looking at Ethernet OEM. Now Ethernet is becoming more and more a end-to-end protocol that's used in the networks. It's coming from the local area network area, and now it's more and more used also in the WAN networks. And so you see that more and more end-to-end circuits or services are built upon Ethernet. So, and even ServNet is thinking of building their new lightpaths over the Ethernet service. So when you have that Ethernet service up and running, then you want to have some kind of service monitoring, and it goes a little bit further than only looking at the status of the network. So not only looking whether the nodes are working or the interfaces are up, but you really want to see end to end whether the service is up and running. And even you want to do it maybe on customer level. So you want to see when one customer has an Ethernet virtual connection on your network, you want to see whether that one is failing and maybe the other ones are not. So it really is about monitoring the end-to-end service, and then I'm going to talk about, well, what is then the monitoring of such a Ethernet service, and then I begin with a typical IP VPN service, where you can think of maybe do something like IP ping or IP SLA on it, and then well, this could be a typical network. I think I can do some kind of, well, doesn't matter. We have this network here, and this is an IP VPN. So when I do, for instance, an IP trace route, I see that there's a flow going through the network. And when I do this IP trace route, this trace route will take usually would take the same path as the normal network traffic is taking. So now we go into the Ethernet service, and then we have some kind of what we call. Yeah, I think maybe this one is working, but I don't know what. Okay, thank you. So now we have an Ethernet virtual connection provisioned over this network. So no IP here anymore and here anymore. But at the endpoints at the customer or the research institute, we still have IP routers there. But when we do now an IP ping or an IP trace route, we won't be able to see what happens on the IP level on the nodes in the NRN network, because there is no IP there. So it becomes completely invisible for us. We just put it in the network, and it comes out at the other end again. Then we can go even a step further, that we have an EVC that even stretches out to the customer sites, and we just have a VLAN that's coming out of a port there, and that's not that unusual to think. Sure, there will be some kind of IP on that devices here and maybe here and there to manage it. But if we would start an IP trace route or IP SLA, some kind of thing from that, it could well be that it took that path to the network. But actually, we were interested in whether the green service was still up and running. So what we actually wanted was, we wanted to see this. So we need something that does that on the Ethernet layer. Well, there are a lot of people that already have thought about it, and they put something into the Ethernet standardization that is called Ethernet OEM. And it's actually it's you can divide it in up to several layers where you can do Ethernet OEM. So maybe I start at the bottom at link layer OEM. Link layer OEM is doing all kind of stuff on the link layer. So it's just between two nodes, see whether that Ethernet link or MPLS link is still up and running there. Then one step higher we have the network layer, and that's we think the most interesting part here. You have the network layer, and that's more doing the end-to-end monitoring, so over several nodes. That's also sometimes called service layer, but we make the separation here with service layer OEM. Service layer is more towards the customer end sites. to make the provisioning of the service easier. So it announces which VLANs are available at what quality to the customer sites. I already told that the network layer maybe is the most interesting part, so I will focus on that one now. So you see that there are two protocols mentioned there. It's the IEEE 802.1 AG standard and the ITU-T Y7031. I will talk a little bit about what is in those protocols. So we have at the network layer OEM, we have you can again divide it into fault management and performance management. And in the fault management, you find things like fault detection, so see whether a service is failing. Fault verification is more that when you see that the service is failing, that you can verify per service that whether it actually was a good how do you call it? It was a good alarm that was sent, so that the circuit has a failure. So it's more on demand probing of whether the circuit really is failing. Then you have fault isolation, is tools to see where in the path the failure is happening. You have fault notification functions that can notify other nodes or other layers of the fault that is happening, and you have fault recovery functions to switch over to other backup paths. Then we have performance management, and what's already is there is that those functions are only implemented or are only specified by the ITU-T specification. Things that are specified there is how you can do on the Ethernet level delay measurements or delay variation measurements or packet loss or throughput measurements. So it specifies some kind of packet formats which you can use to do these measurements. Now I'm going to talk a little bit more about fault management functions that we have here, and actually the first three I'm going to talk about. First, what is the concept of network layer OEMs? These are almost the same between the IEEE standard and the ITU-T standard. Well, here we see a network in an operator domain with several connected nodes, and we have an Ethernet service that is provisioned like this. And what the concept is that you can specify on the edges of the network, you can specify maintenance association endpoints, and in between you can specify maintenance intermediate points, or maintenance association intermediate points, or MIPs. And the idea is that when you send OEM messages, they pass through that path. So you can send messages from the MAP to the other MAPs. Or to other MIPs, so the messages are only initiated from the MAPs. So how would it look like for fault detection? Now we have a Ethernet circuit that has multiple endpoints. So it has four endpoints over 3 different nodes, and the fault detection function is implemented by a continuity check message that periodically sends messages from a MAP, multicasts it over the network to the other MAPs, and when, for instance, an MAP doesn't receive a connectivity check messages from this node for 3.5 times the interval, then it will signal that maybe that node is failing. But it could also be that maybe there was only a problem here, and then this one will still get the continuity check message. So in what you can do here is you send those messages to your OSS PSS system, and in that system you can do already some kind of isolation at where the problem might be, but this is all done automatically. So then we have the fault verification. Sorry. And that's really like the IP ping that you have on the IP layer. So you send an what is called a loopback message to a MAP or MIP, and you just wait for the reply coming back. And if it's coming back, then you know that that node is still or that MIP is still up, that you can still reach that MIP, and when you do not get the message back, then you know that something in that path is failing. Then we come to fault isolation, and that's when you really want to check where the problem is. Well, in IP networks you usually use IP ping, ICMP messages, sorry, with a increasing TTL to see where the problem is. Well, in Ethernet we don't have such kind of thing as the TTL, so it really uses dedicated message that is sent and travels through the whole network. It's reproduced at each node, and all the MIPs and the MAP in the path, they need to answer on that on the message. And if there's one MIP or MAP that's not answering, then you know that maybe somewhere there in the path there's a problem. So it's all very interesting stuff. So then we go to some scenarios. Well, then we looked at, well, would this be useful in a single domain scenario? So that's actually the situation that I discussed just. So we have this concept of sending all these messages, and this is very easy to then when you do this for all the Ethernet virtual connections that you have running on your network, to see whether one of those is failing. But it could be when you have several Ethernet virtual connections crossing exactly the same path in your network. It could give quite a big load in your network. So maybe then it's also interesting to see, well, if we have such well, now we have to flip the network on its side. If we have a network that's running on MPLS, and all those Ethernet virtual connections that were running via the same path are running over the same MPLS path, then maybe it's better to use that one and use the OSS/BSS system to make the link between the Ethernet virtual connection and the MPLS path where the Ethernet virtual connections are running over. So for the single domain, it could be interesting, but it could be solved with other systems then. But then we come to the multi-domain situation. Here we have two operator domain networks, so two NRN networks, where the one is using MPLS TP to run its Ethernet connection on it, and the other one is using PBBTE to run its Ethernet connection on it. So we can't do any, if you really want to do this end-to-end monitoring of that connection, we can't use the systems that were used in MPLS, or we can't use because we can't only use the ones that are used in PBBTE, because PBBTE is only used here and MPLS is only used here. The thing that they have in common is that they have the interconnection on the Ethernet level there. So in this situation, it would be really interesting to use this Ethernet OEM system, so we can really do this measurements from here to here. And what you already see is that I defined all kind of MIPs on all the nodes in the MPLS TP network. But it's also possible to maybe hide some part of your network and only define a couple of MIPs in your network, but you still can give some insight in this party, whether the Ethernet virtual connection in the part of your network is still up and running. But maybe I already told that in the single domain, maybe it is also nice to have. So what if I also want to have separate how do you call it? Separate Ethernet OEM services running on my own network for my internal work. Well, there you have the system of maintenance domains that's also specified in the IEEE standards. It's possible to define different domains for a service, and you see here again the network is flipped on the side, and you see that in the operator domain I can specify a lot of MIPs, and on a higher level. So if you look back on the provider domain level, I can just specify that only the edge of my network here and the other edge of my network is visible on the provider domain level. And I already have shown here that there's also maybe on the customer domain level. So then we get to the customer insight then. That's another scenario where Ethernet OEM may be very interesting. So I can specify MIPs in my network, and other NRNs can do that as well. And when we define a Ethernet virtual connection over that stretches all those networks, with these MIPs I can give the customer, the research institute itself, insight in whether their service is still up and running, and when it's failing, they can do some kind of already see where the failure is happening. And well, actually, until now I was mostly talking about fault management, but all these points can also be used to do some kind of performance management function. So I can also check what is the delay of the part of the network here, and what is the delay when I do a measurement to that point. And very close connected to this, give the customer itself insight and run their own Ethernet OEM systems to see what's happening in the network. Maybe it's also interesting to do some SLA management stuff. With almost the same setup, it would be possible to, on the Ethernet service level, compare what you agreed with the customer and what you actually delivered there. This could be something that is done by the customer itself, but could also be a service that is delivered by the NRNs. So that's also a very interesting how do you call it? Toepassing application. So then I come to the conclusions here. So we looked at Ethernet OEM, and we saw that when it's becoming more and more end-to-end Ethernet, it's really interesting to use this, and maybe one of the few technologies that you can really use to measure end-to-end fault management and performance management. And what I already talked about, there could be a possible benefit in the single domain as well, but maybe there could be also other mechanisms seem to be more efficient there. When you're going to use this stuff, then you really need to negotiate between NRNs on what maintenance domain levels you will specify, where you will place those MIPs and MEPs, and what kind of these functions you will support in your network. So I think that was what I wanted to tell. Are there any questions?
Yep. Thank you very much for your presentation. I wonder how much of your content can be a driver for further development of Persona or similar tools working in our NRN community.
Yeah.
Are there any questions, specific questions to the speaker?
It was not clear to me what kind of interface do you have for the management person. So all these elements that are inside the network, they have the primitives. What is the API for the management plane?
For the management plane, mostly now is SNMP based. Yeah, well, actually, what we did until now is really look into the mechanism itself. So we haven't checked a lot of implementations yet, but we know that a lot of this stuff is set and read by SNP.
Another question? Okay, before we close the session, I would like to make a couple of announcements, as usual. So there are demos performed out in other rooms. So if you are interested, there are still few sessions, demo sessions available. So please check the schedule online and LCD screens to attend. After this session, there will speakers, authors of the posters will be waiting for you, waiting for comments to be addressed. So this poster session will last till 4 p.m. And tonight we have a gala dinner, as you know, and we will be delivered to the final destination with historical trams. We need to be punctual. I mean, we have a meeting at the reception 6:45, and please try to meet this deadline, because trams cannot wait for us. They use the public facilities, so they will not waiting for people. Return buses are already arranged, have been already arranged. Please do not forget badges. Important message. Beer and water will be served in trams. And do not forget about feedback forms. So please provide the feedback to make the Terena conference even better next year. Thank you very much. Thank you all speakers.
I forgot one thing to say in my talk. If you want to experiment a little bit with Ethernet OEM, Ronald van der Pol from Sarah has made a poster over there. Out there, he's already standing there. He made a open source implementation of some of the IEEE 802.1 AG function, so that you can install on a Linux machine or free BSD machine. So feel free to ask him about it.
Thank you, Mark. Okay, the session is closed. Thank you. Beer in a tram. Yeah, that's good. Thank you. Thank you for